As I said you, one of the major criteria of any design in analog is to get the circuit working which has gain. Okay, that is our most important thing, amplification. That is what we do in analog circuit. So we want to amplify an input signal which may be very small. In many cases like in mobile and others, the antenna gives a very small signals and we want to amplify that. So our major activity in any analog design is amplifications. So all our effort initially will be how to do a good amplifier. Now what is this word good? Good means what good? Okay. So we will like to see how do you design a desired amplifier characteristics instead of saying good. Okay. There are, yes, I agree with you, filters for example. But if you see a active filters, there will be some unity gain amplifiers. Gain does not mean essentially, even the attenuators has a minus dB gains. Okay, so in some sense amplification is a conversion of some input to the output in some form. Okay, you have a right valid issue. However, here the circuits which I am showing probably have gains. There are three kinds of amplifiers shown by me. One is a standard amplifier which all of us know. So these are three amplifiers shown here. The first one which you are seeing here is essentially an amplifier in which there is a some kind of an active device. In general it may be n channel device for a MOSFET which has an input and it allows some kind of transconductance through this at the output. So it converts this voltage into some current and through this load current flows in this. Please remember, in a circuit, in a arm only one current can flow. So if this is my output arm, only one current can flow. So whatever is current coming from power supply must go through the driver either. So these two currents must be balancing every now and then. The driver current must be equal to the load current because there cannot be two currents in the same arm. So this device which is shown here shows that IL is equal to IDSN, and whatever I am showing here, the lower part of this device, in case of n channel it is source, is grounded to VSS. Now this word VSS will qualify a little later. We do not say it is ground always. What I mean why we say, because we may not say it is ground always, okay. But in right now let us say it is ground and the load is connected to VDD. So obviously this is a standard amplifier. This device could be bipolar transistor, it could be a MOS transistor, and in any case IR drop here will actually provide you the output voltage. Okay, so very simple amplifier. The other version could be, you may have a p channel device or PNP transistor, and since you want to keep that power supply same positive VDD, so this is then becomes source, then becomes drain for p channel device, and the load is downwards, and same method one can say the output is now. The reason is that I am always saying current can always flow from power supply to the ground irrespective of carriers. Is that clear? Whether it is electrons or holes, though they do move opposite, but the net current, electrical current external to that is always in unidirectional from positive potential to ground or negative potential. That cannot be changed. This is Kirchhoff's law and nothing much can be done on it. Okay, still stands perfect. So this is a p channel device, so same technique. So one can have an n channel device or can have a p channel device, both for amplifiers. And if we make a combination of the two, which is a p channel device and n channel device connected to the gates, we call it complementary MOS or CMOS amplifier. So this is essentially, to some extent we are now saying that each transistor behaves as load for some time. Is that correct? Initially maybe this is driver, this may be acting like a load, after some time this may act like a driver and this may act, or you may say superposition. You have n channel amplifier superposed on p channel amplifier, each acting load for the other one. Is that clear? So this is a possibility which we can use, and the advantage we shall see soon. Why CMOS? Because we have already seen CMOS is one technology which digital has adopted. Till, as I said, technology node right now is 16 nanometers. So since every circuit is digital, which is marketed in heavily, at least I said 20% is analog, that means 80% is digital. So obviously someone who has majority or power will govern, so digital people govern, and because of that CMOS is a standard technology. Do what we may change materials for some reasons, for some device or some circuit requirements, that we may have silicon carbide, silicon germanium, silicon germanium carbide, gallium arsenide, indium arsenide, indium arsenide, gallium arsenide mixtures, many things can be done, but CMOS may still remain. Okay. And as I said many years, for last so many years, 2030 CMOS is going to stick. In any analog design we find there are few parameters of relevance. Three of course are most common, some others we will add later. The first of course is transconductance. What does that mean? From the input voltage, how much is the output current gets modified by the input signal, essentially called transconduction. Okay. From voltage to current converters are essentially transconducting. So the first and most important parameter for an amplifier is the GM, transconductance. We will see what values we get in real life. Then the next very important characteristics of a amplifier is the output resistance. In the case of normal amplifiers which you have seen just now, for example this, this load or this may be a resistor, but in CMOS there is no real resistor there. However, you can connect a load afterwards, so you can have something like this as external load. But the way circuit operates generally in integrated circuit, there is no real resistance put any time. Whatever is the output resistance of this is useful for the next stage connections. Okay. So what the next stage input resistance is the output resistance of the last stage, and that we call as R0. Okay. So in an integrated circuit, not that RL will never be used, but in general connections are not through load, actually load is output resistance itself is acting like a load. So having said so, the second parameter of interest for me is the output resistance for the transistor or the amplifier, which is R0. And the third and the most important for analog is the noise, this, and the word I am keep using this word, very important when we come to noise we shall talk about, is input referred noise. Though noise can be at any node, okay, but we call it input referred noise, and that is very major criteria of design. How much is the tolerable input referred noise, how many dBms or dBs corresponding to given signal, how much, essentially it converts into what value we are more popularly known, signal to noise ratio. How much is this noise at input to noise at output ratio we can get is very crucial for any amplifier. Okay. So this input referred noise is essentially is a basic noise available without external anything, and say if that is what is going to change or increase, then your purpose of amplification may not be as good. Okay. And the most important other than the gain factor, which is the first two essentially gives the gain, second one is the noise worrisome, and the third which is the most equivalently most important from digital, there is a speed, how fast the circuit is working, 6 gigahertz, 4 gigahertz, 5 gigahertz. Here is what we say equivalently bandwidths. How much is the bandwidth, that means up to which frequency gain is constant or reasonable, okay, is we say its bandwidth. So for an amplifier we are always designing for a gain, noise and bandwidth. Is that the three parameters which we wish to control. If we are able to control these three parameters strictly, then I have design done for my requirement. Is that if I cannot control, or it so happens trying to control one I lose something else, then I say Baba, that's with this technology, with this is possible, no more. Okay. That's we say figure of merit, end of it. Okay. Before that how much play we can have, As in the case of digital, I think you are already learning and you know much about, is we can trade off power and speed. Increase power, that means increase currents, the capacitor charges faster or discharges faster, so speed is higher. You reduce the power, reduce the currents, it slows down. Okay. However, we can meet both slightly by adjusting areas. This is the game which we will play in digital. Here we have to play game for gain and frequency. And third, which is not visible immediately, is the noise, which may actually control both. Okay. Okay. And therefore, these three are very crucial parameters in our analog designs. Here is another slide. These are still generic. We will come to it today, MOS transistor a little bit, so that you know what exactly I am talking about. Here is a differential amplifier shown to you. We will actually design and define this semester. There are two n-channel devices with two loads, and this is a biasing current which is called current source, and we have just named them 1, 2, 3, 4 okay, areas. So for example, there is R, when we say constant, there is nothing called constant in circuits or devices or in integrated circuits. R may drift, change. Okay. So one possibility is there is a variation in R. We also said the transistors are identical for DFAM. This is the only statement we make. In reality, M1, M2 may not be identical in many ways. Its threshold may not be same, its size may not be same, W bias may not be same, and therefore they are not identical. So there is some kind of a offset relationship. GM, it will be related to them. So GMs may not be same for either M1 and M2. Okay. So that is another issue which may have to create. And of course, this so called constant current source may not be constant, okay. And if that changes, the bias point is changing. So is the GM and everything else will change. So if you look at these variations, 1, 4 and 5, that is Vt change, drift in this and R values, it may change the operating position of the amplifier. If you look at the 3, that is essentially the offset because of the non-W bias equivalence, then it may increase, this change may increase, actually two devices may be offset by some value. We believe that they are same, but we are not actually. However, do not worry, in real life offset can be cancelled some way or the other. Okay. It is not that there is no way we cannot get rid of offsets. What is the price we will pay? As I increase as I improve anything, I will have to pay for it. And that payment may be in the external extra hardware which I may have to put, or extra power I may have to pump to get rid of some of these. But that is not that we cannot do that, and we will see some of the offset techniques we will use later. 2 and 5, which is essentially again threshold variation as well as offsets in GM, particularly in GM variation causing because of in M1, M2, same way the change in current in the biasing currents may actually lead to change in noise, and noise is a very crucial factor, as I said to you. If you look at the last this one, we say 1 change in R, 2 change in GMs, and 5 change in current, biasing current, all of them can change the bandwidths. Okay. So is that point clear why design is an issue? Because in design I will be given a specification. But please take from me, if anyone gives you, say that I want a gain of 100, you say I cannot design for you. Okay, you say what is the maximum, minimum in between the gain you can expect. Okay, you say okay, in a range of 80 to 100 I am fine with it. So I can design a circuit which may give a gain 80 to 100, but it may not be always 100 or always 80. So any time a specs is given to you, design this, it is not doable. Okay, so a spec must come from a customer which is doable, and that is one say range must be specified. Okay, so I say okay, the minimum gain I expect is 100. So if it is 120, I do not mind, but 100 minimum bandwidth I want is so many megahertz. Yeah, that is the minimum I expect. But you do not say no, it is 2.73 megahertz or 2.73 gig. I cannot do this any design way. Okay, there is no way I can control specific values. Okay, if I try one and then other I may not be able to control. So I always will say you give me some margins in designs. So this is the major difference in the analysis which we do and the design we do. Okay. But to do a design we must know analysis, otherwise how will I design, but the focus should be this, that we have to attain specs within a given range. That is the trick of the design issue. Okay. If you look at the other part which I said, gain and bandwidth, I just said it, but they will come back later also. I will not go into very strong detail, just I will show you there are two kinds of noise, in fact three kinds of noise, but at least two shown here. One is called thermal noise, which is always present because of the incessant motion of carriers, okay, which is called the thermal noise, and there are other names also in thermal noise, related names, short noise and other, but I take it thermal as a common name. And the way we will define when I talk about thermal noise, it can be given by, as we call, 4 kTr volt square by hertz, and this is the function SVF is a noise function, we will define it little later. The other noise which is very dominant at low frequencies is called flicker noise or 1 upon f noise. The word 1 upon f came because the noise essentially decreases with frequency linearly. There are noises now available which decreases by 1 upon f square, okay, post office noise as they call it. We will see that when the turn comes, okay. But see, simple first models are their frequency, as the frequency increases the noise linearly falls. This noise area or this noise is called flicker noise. There is a point at which this flicker noise is exactly equal to the thermal noise, and that is called corner frequency, okay. We can define this later. You can see the figure has been shown here. This is a noise versus frequency. Initially there is a 1 upon f noise at low frequencies, and somewhere beyond fc thermal noise takes over, because this term here volt square per hertz will actually start dominating over, because 1 upon f may go down further and the thermal noise will take over. So we say at the point where thermal noise takes over from 1 upon f, we say corner frequency for noise, and that is given by some kind of this function, and we will see to it how do you control these values, okay. Noise is some way connected to GM, you can see clearly it has a term oxide capacitance per unit area, the width and the length of the transistor, and of course the temperature at which you are working. Of course all noises are generally temperature dependent, okay. So if you are working on a circuit which is at higher temperature 55 degrees centigrade or 70 degrees centigrade, which is a military standard requirement maybe 125 degrees centigrade, in that case your noise will be higher, definitely higher, nothing much can be done because KT dependent, okay. So noise is a temperature dependent, and therefore in normal circuit what will we do to reduce noise? Cool it if possible as much as possible, or remove the heat from the circuit as fast as possible. If you can do this heat sinking, then you can operate the device at relatively lower noise. So where it will be the lowest in real life? If I put a liquid helium jacket everywhere 4 degree Kelvin, then yeah, in my all noise, but then suddenly you will figure out GM also will not be there, okay. So then the amplifier may not be available, but as such noise can be minimized by reducing the temperature or what we call ambient temperature. Do not look at too much into expression which will anyway derive later. Here is a small amplifier shown here. The idea why I wrote those expressions is to explain this figure. What we say that each resistor or a device which also in a way is resistor contributes to the noise, okay, and it gives equivalent current sources across each of them. So if RD, there will be a ion RD average square current shown here, and this is ion device average square. These two currents sources are available with each device and the resistor. So as many devices or resistors you have, that many current sources, noise current sources are available, and noise currents multiplied by resistors available will give you noise outputs. So larger the ion squares or equivalently VNs, then you will have larger noise outputs, okay. Is that clear? And one can see some way they are strongly related to GM, is that correct? And therefore as you look for the gains, as you look for the bandwidths, keep mind that your noise is also getting affected simultaneously. So in many designs this criteria of noise is little ahead and therefore we do not pay so much attention as normal case, but in real IC designs now probably you may have to actually start looking first noise and then see okay now what can I give. Okay. So these issues are very relevant and therefore should be appreciated. This beta of course exactly is W bar related. We will see that the device parameters essentially decides the noise factors. We will come to noise again because that is a very relevant area for analog designs, little more in detail. So if you are an analog designer, what are you looking at? Okay. How much things you should consider? So few things, not necessarily it is all of it, but most of it I have written. Most analog circuits if you see, they have signals alternating, AC signals. Signals are not necessarily unidirect DC, they may be varying but not DC. They are not only plus but they are also minus like an AC signal running on 0 voltage. Okay. That means signals can be positive or negative. So is power supply can be positive or negative in our designs. Okay. VDD and that VSS word can be then minus VDD also, or we call it minus value of power supply or any other value, need not be same. This is called dual rail, one rail at plus, one rail at minus. Compared to digital design, all analog circuits always have dual rail designs because many a time minus VSS or minus value at the lower end may help. Okay. In the case of analog, I have already shown you IV characteristics earlier, but maybe we will show you again. The biasing point where you bias decides the dV0 by dVn, okay, that is the gain. So where do you bias is very crucial because that will decide the GM, that will decide R0, that will decide everything for you. So bias point control is very very crucial in analog designs. So as I said, if that drifts, everything drifts. Okay. So one is to worry about bias points operating. In our second year course we always thought okay एक बार एक resistor लगा दिया ये हो गया bias, fixed bias कर दिया, ऐसा नहीं है. So you have to do some tricks to keep that constant. Okay. Also for normal amplifiers we do not want gain to vary because otherwise for some signals it is something, we want gain to be constant, or to say VO Vin characteristics in the region of interest should be linear, dV0 by dVin should be constant, linear. Okay. So that is one important thing and therefore these circuits are many times called linear circuits because there we assume gains are constant, dV0 by dVin relationship is linear and therefore the circuit themselves are called linear circuits. Okay. It does not mean that in real life there will be everything linear. In fact the whole life of every one of us or every creature of this world is extremely non-linear. How much non-linearity you can control or how much idiosyncrasies you control, that is what your outputs of nature will be. Okay. Every one of us have different idiosyncrasies, we are very non-linear in nature. Same inputs does not evoke same response. Okay. Some may be right now feeling why he is teaching but still sitting here. Okay. Some may say he is giving too trivial. Everyone has that same thing I am saying, but you may have different perspectives. That is what I say non-linear issues. Okay. So reality is non-linear, so how do we control non-linear systems? This fourth, as I said already said, all analog circuits are extremely noisy, so they should be somehow made noise tolerant, but they are very low noise tolerant. Small change will immediately shown at the output, do not do anything, it will come out. Okay. So that is the one worry for a designer. We must see to it that the drifts are small. I have just shown you earlier figures that drifts can cause what? Everything can be changed. So drift has to be minimized is one consideration in every design. Anything which changes is a drift. This value drift. It can be plus or minus. Drift can be either. Okay. Standard cells are essentially block design a priori, design, fab, test it, and then their square block is shown to you, AND gate. Two inputs, one output, this currents, this speed, and internally what is not told to you. This is the standard cell. Okay. There is no real problem with digital circuit even if I reduce the power supply. We are going to 0.6 as I say, okay, maybe 0.4 someday, because we are happy that 1 0 still can be reachable, so it is okay. In analog, if you reduce the voltage, the currents reduces and GM is nowhere then, okay. GM is essentially proportional to I. What formula it will, root or a square or half, whatever you see later, but it is function of IDS. Now if you change this, the current goes, your gain goes, bandwidth goes, everything goes, and then now as I say in the new technologies, when you are asking us to work on a very low biased circuits, we insist that at least do not tell us that you will work on 0.4 volt. We will have our own power supply and we will work on our own circuit part. So there is a power management unit on every mixed signal, because analog cannot function at 0.4. Okay. It's you are closer so much to the noise that I will only see noise. Okay. So I will not like to work at very low biases, though it is fantastic because it will give low powers. Okay. So designing a low power analog is itself a big challenge, because that is the game one has to play, because overall chip cannot be one part is heated so much and the other is not so much, then there is another issue will come in this temperature gradient it will set and it will start varying the digital part faster. So there are issues in placement of analog blocks also, where do you keep them. Okay. So there are many issues when you put analog with digital, because as I say low power is the game, everyone wants low power, which is true, means low power is the game these days, or rather I always like to call that low energy systems. We are not very keen about voltages or powers, we should be worried about energy. Okay. Essentially I am saying you can have large currents but lower voltage, or larger voltage, lower currents, still energy and for a shorter time. So as long as you manage that, you are still in a low energy systems, and that is more important. So to summarize what I said, to stabilize your DC biasing, you may have to either increase the power supply or tune the bias currents, vary it some way. Okay, we will see current mirrors do that. The word PM is very important, we will see, come to it later. Phase margin, one of the major worry in analog circuit is phase relationship between outputs and inputs. If you have seen a transfer function in a control theory, we keep talking of margins. Sometimes in time scale we say jitters. All of us are jittery when something does not go well that we want. In circuits, when they jitter, it gives noise, phase noise. Okay. So what we do is that may change the stability of the system. So you may have to do some kind of pole compensation, pole zero compensation, or some way you must split the poles or whatever technique. Feedback systems are therefore necessary, and you must get the stable circuit. We must work on architectures which are constant GM, because if GM changes, as I say, everything changes. So any design you do, see to it your block has constant GM, that should not be. I may change the value of a GM at my will, but once fixed it should not change. That is what design is all about, constant GM, which also is required for good stability. Now we know this offset part which I said, if the two arm of the circuit has equal offset or equal change, in a differential mode something which is common may get cancelled, and that is what the diffam's theory is all about, and therefore offset can be minimized, if not making 0, at least by using diffams. Okay. And we will see that is why all differential amplifiers are so common in analog designs. For comparator designs, you need very high gains so that any degradation would not affect much its operation, because comparator shifts A to D, it converts. Okay. So the gain of a comparator should be very high, so that any marginal change should not reflect 1 0, it should give immediately, and such degradation effect should be minimized. So when I say gain, I am suddenly looking at GM, and when I say look GM, I go upward and see everyone is hurt by change in GM. So the issues are essentially device related and circuit related in their interactions. So when I design, you must remember that design is not just analysis. A slide I think I made other day. What is circuit analysis in my opinion? Someone asked me, well, we can have a larger circuit which can be decomposed or reduced into smaller blocks, and each block is manageable in designs. Okay, that is analysis how we do it. We do not solve simultaneously huge network. You can solve on a SPICE or a simulator, but normally when I analyze, I do not have such large papers to write so big expressions. So what I keep doing is use blocks, see to it that its input output always matches. That is the trick we use, and always reduce into blocks and design it. And these blocks should be designed with very simple models for transistors or any other device we use. If they are too complicated, you cannot do circuit analysis easily. Okay, so you need to have very simple models, okay, but relatively accurate, because otherwise I calculate gain 100 and it comes to be 10,000, then I am nowhere. Okay, so it has to be relatively accurate but much simpler to handle. So why do you really need then the so called simple models? Yeah, they do give some values which can then act as a first assumption values for large signal or large value analysis. So where to start? Okay, that is the issue. Each circuit has one unique solution. This design, this analysis, if you show me this is input, this is output, this is how it relates, unique solutions. Now if I do a design, how it differs? In most cases you synthesize the design by your past experience. That is why to protect this word IP has appeared. If I design, it is mine and you cannot pay for and take it. So this is the from the past experience, and since one does not know exact solution, you do a lot of iterative solution. So you actually have to do extensive analysis to really design a circuit. When you say extensive, which means by manually it is very difficult. How many times I will do 100 times same thing, just tweaking things? So it will be very difficult. So I need some support from other than me. So I will see what it is. Given a specs, there can be many solutions. Whereas in the case of given a circuit, solution is fixed. In this case there is a requirement and I may get through many ways, okay, and that is the designer's issue. Now one interesting feature which I wish to tell you all as an engineer, if you want to become good, all engineers require skills. Okay, engineering is not only analysis. Engineering engineers should be good designers, and they require skills. Now how they can be achieved? And the word I used is Einsteinian way. What is Einsteinian way? Einstein was once asked that when he was doing problems in general relativity, one of his student in his class, or rather his colleague that time, he asked him, how do you really solve such a intricate complicated problems, or how do you approach that? He says, just by doing it. So to attempt anything, just do it. That is the only way you can do some things. Okay. As long as you do not do it, you do not know what to do it, and therefore you must do it. That is the Einstein way. So please follow. Your failures are good enough, they will teach you many more things, and next time you will be more accurate and more correct. Okay. So this is my suggestion to all those who wish to remain in, even in finance valley this may be equally true. Some of the building blocks which I am going to design in this course. I may design current sources, current mirrors, single stage amplifier, differential amplifiers, operational amplifiers, variety of operational amplifiers. There may be a cascade op amps, there may be, what is OTA means? Operational transconductance amplifier, GM related. So OTAs. Then I may design comparators, voltage references, I did not specifically say the lower one, why I said I will show data converters. This part though is required, since there is a mixed signal course going on, I will not talk about ADCs and DACs in this course. Okay. I may instead talk about oscillators and frequency synthesizers, PLLs, maybe I will talk more. And then the switch capacitor circuit, these are essentially also part of mixed signal, but since they are filter realizations, we will talk about some simple filters, if not very complicated filters, active filters as I say, using switch capacitors, okay, which is what technology will appreciate. So this is something blocks this course will address to. Hopefully by the end of the course you learn enough that all of this you yourself can design to a given spec. Okay. So please remember, we start always with trivials and then build on this. This is how designers do. Do small, pakka, another small, pakka. Keep doing till you reach your ultimate aims. Okay. Many of you have already done this, or hopefully should have done in your second year course at least. Okay, so this much so far is more generalities. We say okay, this is what analog design is all about, and as I say, our course name itself is CMOS. That means there is a MOS transistor sitting somewhere. Though I know again third year student यहाँ होंगे जो गलती से होंगे यहाँ पे, I have taught them devices, so they cannot say MOS device was not taught, others can. So उनके लिए जो others may be here, I may start with little bit of basics on MOS transistor, because I keep saying you analog design is more between interaction of device and a circuit. So not knowing devices will not help you in a good analog design. Is that clear to you? Whereas in digital you do not need to know device technology or anything, in fact nothing you should know, you can still design. Okay. The best designers who do not know anything, so they design better. The problem with designers is essentially, I said it is a iterative or too long a process to do. Please take from me in analog design, what is the problem? There is a very famous story or famous statements made in many books, many journals many years ago, that if you put n number of monkeys, say 100, and give them pen, pencil, paper and ask them to sketch anything what they do, even then they cannot write a legible book irrespective. They say they are our ancestors, but even then they can, even with hundreds of them. Same way, if you ask a monkey who is related, why a monkey is used, because they are next to us, so okay, if we can do, probably they also can, is the, if you ask a monkey and give him a spice tool and say design this circuit, he may keep putting hit, at no time an optimal circuit output will come. So essentially in space, that probably may happen in digital, due regards, but in analog you have to use your brain. Manual intervention is a part of analog design. Okay. So intelligently only you can do things. Okay. If you want to leave this, leave analog. Okay. Because that's the difference. I won't say, I mean, as I say, I'm just overreacting on that, but just to say a fun of part in that, that analog designs requires knowledge of technology to a great extent, much more devices, and of course your circuit background has to be always good for any circuit course in electrical engineering. Okay, so we start with the basics of MOS transistor quickly. Today maybe we will finish that, so that next time we start with the real amplifiers. A MOS transistor, as I say, circuit view of a device is very relevant to us. For a device, first we will talk and then we will say how circuit people realize it, what for them is the value here. Okay. I have only a MOS transistor, so for me I say okay, I have some substrate, I created some regions, I have some gate, some drain, some source. Which technology can give me? So I got a MOS transistor, but how does it work? And if it works, how a circuit man knows how does it work? That relationship, what circuit wants from a device, is what this few some 10 sub 20 slide will show you. How does specs of a circuit is controlled from the device parameters. Okay. We will not go further down how technology manages that, maybe that is also relevant someday, if now at least today, but it is okay. So here is a typical MOS transistor shown to you. This is my substrate, okay, which is p type. So it is an n channel device shown to you. I have two regions diffused in that or implanted in that is source and drain n plus. This is a two dimensional picture, but as I said you earlier also many times, MOS transistor is a three dimensional device. I don't know, I don't have anything, maybe this, okay, at least it has third dimension. So if this is my source, this is my drain, this width is the third dimension. So what you are seeing is only this cross section, but there is a width part in this, okay. So that is called W, this is the length, this is W. So a MOS transistor is not a two dimensional device, as in most cases bipolars are. Of course the current bipolars are also not two dimensional, but earlier what we used to do PNP and PNs, they were only two dimensionals. Now MOS transistors are three dimensional, however they are four terminal devices, not just three as one thinks. That is the difference we should understand. So the first terminal is source, the other terminal which is output as we call drain. On this n regions there is a thin insulator layer put here, in 90% cases or 95% cases is silicon dioxide. Of last 15 years silicon dioxide has been replaced by hafnium or hafnium nitride oxides or zirconium. We are trying many high K dielectrics when the channel length goes down, okay. But assume it is a good dielectric, and for most purposes we say it is still silicon dioxide unless said otherwise, okay. Now this is SiO2 or whatever insulator you put. What is the advantage of insulator? Insulator does not pass any DC current, okay. So it is a good insulator. Typical insulation strength of a dielectric like SiO2, it has a 10 to the power 7 volt per centimeter as the dielectric field at which it will break down, okay. Air breakdowns are 30 volt per centimeter, so you can imagine what I am talking about, okay. So this is my gate, and there is a substrate contact which I call bulk B, sometimes I call S once a while, but since source is there S, so let us call it bulk. And so there are four terminals in a MOS transistor. If you show a equivalent circuit for that, this is drain, this is source, gate is separated from this because of insulator, and this is my bulk contact, okay. The symbols are known, if the arrow is in it is N channel, arrow out it is P channel, okay. If it is a P channel device, this will be N substrate and P plus source drains. The only thing will happen is whatever voltage we apply in N channels, the opposite polarity should go for P channel for the similar performance. So the case 1, Vs, Vg, Vd, Vs, Vb all are zeros. If everything is 0, there is no current between drain and source irrespective. No current means no current, because Kirchhoff law says if there is no source there is no output, okay. Unless of course you can say noise, but that is source, otherwise there is absolutely, if everything is grounded, no outputs, everything is 0. So we say transistor is off, nothing is coming out, okay. In current technology node say less than 90 nanometer 2 or less, even for that this is valid, because Kirchhoff law cannot be faulted. At no supply, no currents irrespective, okay. There are cases maybe smaller current because something else, but otherwise if voltages are grounded, no currents. This is a trivial case but very relevant case to say in real life, therefore device can never be switched off. Is that point clear? Because these conditions can never be met. Is that clear? Why I showed you this slide? Just to show you in reality this case cannot be achieved, okay. Though I mean it is possible, you can always take a transistor and ground and check, okay, but in circuits this will not be relevant case, it is called trivials, we will not go for trivials. The case 2, let us say VGS is 0, so gate is still, firstly we say ground source. So what we say, source is our reference voltage, it could have been anywhere, but over the years right from Shockley down everyone thinks source is, why the word source came in the device here, it sources the carriers, okay, N or P whichever way, N channel it sources electrons, in P channel it sources holes. Drain D is called because it picks up, it drains, okay. So that is why it was given a name drain. Now this word gate essentially means if you open or close something else should happen, the output currents. So it was given a name gate, and this B has to be given because it started with the bulk substrate where we say B. So right now we say Vs is 0, we also say bulk is grounded, but we say we apply VDS, no gate voltage, no source voltage, no bulk voltage, but we apply VDS which is positive, let us say. IDS is 0 in ideal conditions, you may find that there is no, since gate is 0 we thought that it should not give any current to you, but in reality there are two diodes sitting here, NP, NP, okay. If I apply 0 0 bias it is still reverse bias, and if I have positive VDS and 0 here I am having a stronger reverse bias. So both diodes are reverse biased, okay, and a reverse bias diode gives reverse saturation currents, is that correct? Since they are giving a reverse saturation currents, there will be a current from source to drain which is called the leakage currents. The off state is always normally recognized when VGS is 0, we say when VGS input is 0 no current, we say off, but in this case VGS was 0 but some finite current, maybe very small, picoamps sometimes or nanoamps, okay. In present case it is becoming tens of hundreds of nanoamps reaching microamps now, that is our worry now in 11 nanometers, 16 nanometers. So this means that there is a leakage path, this we normally do not want to consider in analog design because we say it is a very chota current, but in digital this may hurt your health, particularly in DRAM designs this is what it will kill you, okay. So one must say that VGS 0 normally transistor should have been turned off, but in now newer technologies this is not necessarily can be called turned off, okay. As I say it is called problem area which is called partially on case, okay, is that okay? VGS equal to 0 normally one believes device is switched off, but if VDS exists there will be a leakage current which is essentially always available. So this is another problem which digital people are more worried, not that we are not worried. So this is a issue which we will not deal too much in analog designs, okay. Now here is the case 3, I have Vs grounded, Vb grounded, fine, Vbs is 0, I apply VGS which is finite, that means finite means it can be positive or negative but not 0. This is equivalent case of a MOS capacitor, if this is grounded, this is grounded, this is grounded, it is like equivalently saying you have a MOS capacitor, metal oxide semiconductor acting like a MOS capacitor. So obviously a MOS transistor theory must actually emanate from the behavior of a MOS capacitor. So here is a MOS capacitor shown, 3 voltages I can apply to Vg, one I can apply negative, other I can apply positive but small, and third time I will apply positive but relatively large value. So 3 values I will choose, one VGS negative, second I will say VGS positive but small, and third I say VGS positive and large, relatively large, do not say large means 100, larger than normal, okay. Okay, so first we say VGS negative, If I apply negative voltage on this metal plate, please remember this is metal, can be silicon, also act like a polysilicon can act like a metal, therefore it is a metallic word we use. So if I apply a minus Vg on the metal plate with reference to the bulk which is grounded, then the Gauss's law does not like this system to remain like this, एक plate पे charge. Okay. It says that across the loop of Vg to the ground, the net charge must be 0. I mean that is the system must be in equilibrium. Okay. If that has to happen, there is no charges in insulator, that is what we said right now. So if there are no charges in insulator, then whatever voltage I apply which creates a charge minus Qm on the gate, I must get opposite polarity charge in the semiconductor which is exactly same but opposite polarity, such that Qm plus Qs must be equal to 0, because the net charge around the loop should be. आपके 10वीं 8वीं से ये सवाल आपको बार बार पूछा जा रहा है, इलेक्ट्रिकल में एमटेक आने के पर भी यही सवाल है, nothing more. Okay. Is that okay? That means if Qm is negative, Qs has to be positive, which is, now how do I get a positive charge? One sees that the device started with a P substrate, so it has a certain number of hole density already available to you, but this is universal everywhere, constant Na is QNA. Okay. Na is the doping concentration in substrate, so those many holes are available everywhere, but at the surface I want additional holes, because that is what you said, minus Qm requires additional positive charge. So some way the holes must start coming near the interface, the word is interface between SiO2 and silicon, or insulator and silicon or semiconductor. The line here is called interface. At the interface you must get extra holes. Now from where they can come? This substrate is good enough for you, it will start providing larger holes at the surface. But does that mean that the substrate will get depleted of holes? No, battery you have applied, battery will give you those addition. So because of this, why this can holes have to go upwards? If you look at very carefully, if this is minus Vg with reference to ground, which is the direction of electric field, upwards, plus to minus. So obviously holes move in the direction of electric field, so holes move up. Okay. And the additional holes which we are asking will be actually coming from power supply, so that the thermal equilibrium value of concentration in P remains constant, though holes are actually picked up from the substrate itself. The loss will be supplied by the battery or whichever go up. Now these many holes will only come as much as the charge you put on the metal, so every time equilibrium Qm plus Qs is constant is maintained. So if I have larger minus Vg, then what will happen? Larger holes will come. So you can say larger negative voltage I apply, larger accumulation of holes starts at the interface. This is essentially accumulation mode. We have accumulated holes, we have a P type and we are accumulating positive charge. So we say we are in a region of accumulation mode. So in a MOS capacitor with P substrate with minus VGS, you are always in accumulation mode. Battery always supplied, charge cannot be created from air, so it has to be taken from battery. Now the third case I said, or second case I said, VGS is positive but not very large, very small amount but positive. Now if I see that very small positive value, okay, let us look at this. If I apply VGS positive and small, so I am putting small Qm at the metal. Now by Gauss's law we now expect semiconductor interface to get negative charge, because Qm plus Qs is constant, is 0, is what Gauss says. Gauss is a god for us, if he says so, we agree with it. Okay. Yeah, almost so many years no one has proved Gauss law wrong, okay. Not even perturbation on it. There are many things in weak fields, strong weak fields, many things are coming boson, toson, but no one has challenged Gauss's law so far. Okay, so if Qs is negative, but the substrate is p type, substrate is p type. Now I want negative charge to occur. We said okay, if you look at this way now, the electric field in semiconductor is now downwards, positive VGS, so field is downwards. So holes can move in the direction of electric field. So holes near the interface actually move away. As soon as in a semiconductor positive charge holes move away, what we say, it gets, that region gets ionized with a negative acceptors, and this region is depleted of free charges of holes. Is that clear? Therefore the region is called depletion region. So we now get into this, that we see depletion region. Now this depletion region will enhance because it is a charge density issue. If you increase charge, the charge area is same, so charge density of QM increases. If QS has to increase, its thickness must increase, because otherwise equivalent charge density cannot be created. So larger the positive VGS, depletion layer thickness or width as may be called will also enhance, okay, also enhance to get same charge as you are putting on the metal. So you remain in depletion as long as that condition is happening, that QS is to be supplied through depletion charge, okay. Okay, so this mode we will call as depletion mode. As I say, many of you have learned, this is recapitulations because we need to understand device little better for analog. Let us say VGS is further positive and little better than substantially higher. Now this value how much we will see later when we say it is more than threshold, okay. That word threshold is what we want to define now, okay. Certain value of VGS, suddenly we find things will change, and that we are exceeding that voltage right now as if, okay. So if you apply VGS positive large, relatively large, still keep VDS 0, VS 0, VBS 0, fair enough. So you are still a capacitor and you say VGS is large, large positive charge requires large negative charge. So what could have happened, that this in thickness of the depletion layer should keep enhancing, because what is the depletion charge, can anyone say? I have already written somewhere, if not, oh yeah, here, QNA XD, XD means depletion layer width, this. XD increases, Na is constant, so QNA XD keep on increasing to adjust the extra charge you are asking for. So the semiconductor charge is increasing with increase of XD in depletion. This surface potential psi word, which I have not stated somewhere, maybe we all can use a fresh sheet. This you should understand something like this. You have a capacitor, if I apply, this is semiconductor, this is insulator, if I apply some voltage, call even V, across this is insulator, this semiconductor, V must be equal to Vox plus semiconductor potential. This is Ohm's law, your divider, you apply voltage, two areas, part divisions, okay. So obviously the potential in the semiconductor is defined in terms of psi s, and potential across oxide, which we want to find soon, is called oxide drop, okay. So if I increase, say let us call Vg, either this will increase or this will increase or both will increase or one of them will increase, is the game we are trying to play. Is that correct? Is that point clear? Either each one of them will increase or both may increase or both may not increase, which are the cases of relevance, okay. So this potential drop between two regions is, we call it surface potential. Why it is called surface? Because charge is only near to the interface, so potential will change only where, by which law potential appears, because of charge. Which law is the very famous, which relates voltage to potential to the charge? Poisson's equation, okay. Poisson's law says d by dx is minus rho by epsilon. E is the electric field, x is one direction but multi-direction. rho by epsilon. Epsilon is the permittivity, rho is the charge density. Okay. So larger the charge, larger is the electric field is minus dV by dx. So larger the field, larger is the potential. Is that clear? So we say voltage increase, surface potential can only occur when there is a charge available to you. Is that correct? This is Poisson's law or Poisson's equation. So because of these, as I say, fundamental Maxwell's equations which are still standing strong, electrical engineers are strong. Okay. So now if I say, if I keep increasing VGS, psi s will also increase, but I figure it out that there is at some potential VGS equal to, call it Vt now, okay, this surface potential becomes what we call as twice the Fermi potential. Some other day maybe device theory may be more detailedly talked, but not today. And Fermi potential is given by kT by q ln Na by Na. Na is the intrinsic carrier concentration, Na is the accepted concentration. So if larger the Na, phi f is larger. Okay. So for a, when psi s reaches 2 phi f, one can now say that this 2 phi f xt becomes maximum. Actually we will see this is only 1 phi f should have happened, but we say okay 2 phi f xd becomes constant. If xd becomes constant and maximum, then the charges due to depletion layer are fixed now, but you are increasing VGS beyond that value, then what will happen? From where? Because depletion layer cannot enhance now. You said it, so that is the way definition you are putting. That means there must be another source of negative charge. This additional source of negative charge is always available day 1 actually, but was not so dominantly talked initially, but now suddenly we realized, we figured out that every semiconductor, whether it is a depletion layer or normal thermal equilibrium areas, electron hole pairs are constantly generated. Is that clear to you? This is thermal generation, nothing I can do, recombination is constantly done. That is why NAs are constant, so many holes can be given. Okay. If law of mass action has to agree every time, thermodynamics cannot be violated in thermal equilibrium, then electrons and holes are going to be created everywhere. Even when VGS was smaller, positive, there were hole electrons there also in the depletion layer, here also there were hole electrons. What has happened there? Which side, because of the electric field, which carriers in this upper region, let us say the other region they will recombine because this is a neutral region. In the depletion region, the hole electrons now see electric field. Okay. Which is the electric field? Downwards. Which carriers will move away? Holes. So the electrons can be made available. But at this time we say electrons are not there very much. Why? We said because this electric field is so small that they could not separate whole electrons before they recombine. They are recombining everywhere, so is in the depletion layer. The electric field which could have separated, what is the electric field charge? It gives a force. Is that Q into this is the force, Q into E is the electric force. If your E is smaller, the force on carrier is smaller. So before they separate, they combine. Okay. So if they recombine, there is no additional electrons available to you because whole electrons recombine. However, now when you have increased VGS sufficiently, this electric field is very high because that is what VGS you applied, psi s is very high now. Okay. At that electric field, now you say depletion layer is not increasing, fine, but these electrons and holes can be separated because of additional higher electric field in the semiconductor surface. The holes will move downwards and electrons will move which side? Towards the interface as they separate. So more and more electrons start getting near the interface as you increase VGS. is that correct? Because now depletion cannot give you additional negative charge, additional charge must come because gauzes will not allow you to do otherwise, and therefore negative charge must come from free carriers, electrons. Okay. You started with a p substrate, you created a layer of free carriers, electron carriers. So you say you are inverted. P type, the layer at the top or interface layer is now n type, okay, and therefore you say you are in a region of inversion, is that correct? So larger the VGS now you put, larger will be inversion charge, because and that will be supplied by whom? By this thermally generated carriers which get separated. Now if I solve such Poisson's equation for this, one can see by, of course as I say theory I will not say, the inversion charge due to this thermally generated case is proportional to e to the power q psi s by kT, which means very small change in psi s can create larger negative charge. If you look at my this expression for depletion, q n Na xd, but xd is proportional to psi s, but which relationship it is showing? Root of psi s. The earlier depletion charge is proportional to root psi s, but inversion charge can be created e to the power q psi s by kT. So obviously exponential functions are stronger than root functions. So you do not need now too much change in psi s to get this additional bulk charge or called depletion charge, but that additional charge may now come from the electron hole pair separation, which is going exponential with change in psi s. Okay. So all the additional charge will be now supplied by these separated charges, free charges, and therefore depletion layer will become constant with a pinch of salt. It will keep increasing a bit of it, let us say 0.1% is from that and 99% from that may go. It is not that it will not, but ratio as you say, all of it is now coming from free electrons available through inversion layers, in the inversion layer. This is the crux of MOS transistor. Now we say VGS equal to VT, this occurs, the definition we said that at psi s becoming 2 phi f. Actually when psi s becoming phi f, the material will become intrinsic. You can substitute this value and you say material will be intrinsic. So it will not p type there, at the surface it is not p type, so it is intrinsic, but then there are very few electrons. So we do not want that many, we want larger number of, how many electrons I say is good enough for me? At least as much as the holes below there. So if this electron density is same as what the holes density I started with, I say I have sufficient electrons available, so I say good inversion layer, and that word good we say strong inversion. So from psi s equal to phi f to 2 phi f, inversion is already available, but very less number of electrons available. As you reach to phi f, huge number of electrons can be created, because it is an exponential function. You can see exponential function, initially it rises slowly and then shoots up. That procedure is same here. So initially you see lesser charge, but then it shoots the larger charge. This fact is being utilized here, that at little bit higher psi s, 2 phi f is the number we gave, the depletion layer now will become constant, whatever for 2 phi f, and we will say rest of the charge will come from the free electrons generated through thermally. That is why we say threshold voltage is defined at that point where psi s is 2 phi f, is that correct? It is called strong inversion. Now there is a catch there, between psi s equal to phi f, psi s is related to VGS, VGS equal to psi s plus Vox. If psi s changes, we know as VGS changes, psi s is changing. We say between phi f and 2 phi f, device is still not off, it is on. Is that clear to you? Why it is on? Because electrons are made available to you. This means this region is called weak inversion, and this is also called sub-threshold region. One of the way analog circuit will be designed is using sub-threshold characteristics. VGS less than VT, but it is not switched off, it is not 0. there is a weak inversion going on, and that region itself can be utilized in some devices, some circuits. Most cases will not use it. We will see that psi s is 2 phi f, strong inversion is set in, more and more carriers will come from VGS now, all of it go to psi s, and psi s will increase as much charge as you want on the equivalent of Qn. So the way MOS capacitor works, and therefore MOS transistor works, is that there is a threshold voltage at which this can occur. Is that correct? This, since at this, the, as I said, this figure, since this channel can be created somewhere here, if VGS is positive like this and VDS is also positive, then there is a this is a like a resistor N channel, N area is like a semiconductor N bar, some conductivity it has, this is source grounded, this is drain positive voltage, this is like a piece of semiconductor with two contacts. What current it will flow? Ohm's law, V is IR, depending on the R here, current will flow. So a MOS transistor gives you a current which is proportional to V, which is very interesting, okay. But later we figure out it is not linearly going, so then what makes it change, we will see next time. I hope that those who have not done device course in their careers, or not done the course the way IITians think they should do, I said the initial availability in a capacitor is essentially because of the minority carriers. However, when I make a transistor, I have a source of electrons, infinite source, so the electrons will actually come from the source and not from the minorities. Minority will keep that channel, but the current which will pass will be carriers supply, otherwise one time these carriers will be swept off. So the carriers which are required to maintain a channel will always be supplied in a transistor by source electrons, that is why it is called source. I will keep giving you electrons as many you want, and this is N plus means heavily doped infinite carriers, okay. So I will keep supplying you any number of current carriers required, but the channel will be maintained essentially because of the VGS minus VT available. Is that clear? This inversion cannot be done from source side, it can only be done from gate side. So the inversion layer maintenance is because of the minority charge, but the charge movement is supplied from source to drain by the source. Is that clear? Oh, all the carriers there are thermally generated, there is nothing else. Okay. Inversion layer is always thermally generated carriers. Okay. Is that okay? Metal is insulated by from the semiconductor. Na? There is a oxide, so nothing it can do below. Is that clear? No, how can the current can move through insulator? Oh, you mean like this? Oh, but that is the circuit anyway. Circuit, that is what I say. Finally, carriers through source from where it is coming, through battery. There is no other source of carriers. Carriers can only appear from a battery. There is no other source. Okay, is that okay?